So now we're going to talk about solving exponential and logarithmic equations, which you kind of already have done, but this is going to be a little bit more formal. We're going to do a bunch of examples to make it pretty clear what's going on. So to solve exponential equations, use the log, which is the inverse, to undo the exponential, and vice versa. So if it's a log equation, you use something called exponentiation, making something an exponent to undo the logarithm. So you're just going to see what these are. Best way to do it is just kind of show you some examples. So here we go. 2 to the x equals 32. So by inspection, what you could do is, you could take the inverse of that. What's the inverse of 2 to the x? By a log base 2, right? And now this is the exponent. We know the log equals the exponent. Log base 2 of 32. Now, it turns out that the answer is 5 because 2 to the 5th equals that, but if you take the log base 2 of 32, you're going to end up with 5 as expected, okay? Now, this next one, you've got two natural logs that are set equal to each other, and so what you can do is, well, could you write this like this? That is, set them equal to each other. And this is where the exponentiation comes in. How do you cancel this out? Well, it's a log base e. That's what natural log is. So you exponentiate base e. That cancels out the e in the natural log, leaving you an x. E in the natural log, leaving you a 3. And you're staring your solution in the face. Sorry. All right, this next one. If you're presented with something like this, probably the easiest way to do it is to write it in exponential form. Reason being is you can't take the log base 3 of x. It's an unknown. But you can figure out 3 to the 4th, which is 81. Same idea here. Natural log of x, so this is log base e, right? So two ways to go. You could rewrite it in exponential form, or if that bugs you, you could compose it with its inverse, which is e to some power. Exponentiate base e is what it's called. So x equals e to the negative 3. In this case, for accuracy's sake, I'd leave it like that. If you really want to, I suppose you could write it as 1 over e cubed, as a little reminder what negative exponents do. All right, e to the x equals 72. How can we get rid of the e to the x? Well, couldn't we take the natural log? Because what's the inverse of an exponential base e? Why, a log base e, right? Now, can you take the natural log of 72? The answer is yes, and you get right around 4.27. Now, please get in the habit of going to 3 decimal places, rounding or truncating. So technically what you get is this, okay? If you type this in your calculator, use Desmos. When I say round to 3 decimal places, I would say that would be, right? That'd be rounded. And then truncated. Now, truncated, the reason I'm mentioning this is because if you're going to take calculus, AP calculus at least, they're going to expect you to go to 3 decimal places by automatically rounding or truncating. The reason I like truncating, to truncate means you just cut off, is you just write the first 3 decimal places and stop. You don't need to worry about rounding, because even rounding, you could screw it up, right? Now, here's where things get a little bit tricky. If you want to solve this, you're going to have to get rid of this 2 to the x, which means you're going to have to take a log base 2. But you want to isolate the exponential. That is, you want to get 2 to the x equals, you want to get that 2 to the x by itself. So we want to divide by 3 first, which is that. Now we can take the log base 2, and that's going to equal the exponent of 14. Now remember, on Desmos and any other calculator worth its salt, you can take a log base of whatever you want and find the answer. So that is basically what you could do. So log base 2 of 14 ends up being, what does it end up being? So it's my preference is to truncate, so I'm going to write 1.829 and be done with it. Okay? All right. Same idea here. You still need to get the log, the exponential rather, by itself. So thinking about this, it's like a linear equation, isn't it? 4e to the 2x equals 5. Then you divide both sides by 4. Now it just turns out that you could write 5/4, or you could write 1.25 because you don't have to round to do that. Then because it's a base e logarithm, you take the natural log right? Now, when you do that, it cancels this out. That does still mean you've got a 2x equals the natural log of 1.25. And then you still need to, at the very end, you still need to divide by 2 to ultimately get the x by itself. Now, if you left this as the natural log of 1.25 all divided by 2, I'd be fine with it, right? I would expect that you can put that in your calculator decimals if you wanted to. If you're curious, that ends up being 0.111. That'd be truncated. Okay, same idea here, slightly different logarithm. So we're going to add 4 to both sides. Then we're going to divide by 2. Because in order to get this by itself, you need to actually, it's okay to write a decimal here, or you could write 15 halves. You need to get the exponential by itself. So then we can take a log base 3, or we can rewrite this in log form is really what we're doing. It's going to be a log base 3, and that's going to equal the exponent of 7.5. Okay? Okay, this, right? Now, this is where doing all the work and then actually simplifying at the very end, or typing everything in your calculator. So you'd agree you'd have to add 5 and then divide by 2. So you'd have the log base 3 of 7.5, which is a number. We're not going to calculate it quite yet because we're going to calculate it all at once, then divide by 2, because it's going to be more accurate. We don't write this out because we'd have to round it to write it. So if we do it this way, then we can save ourselves a little bit of grief. And we get in the end 3.417. Reason we want to wait until the very end to type all this in is we don't round on any intermediate steps. It's more accurate. Okay, this is different because this has an e to the x and e to the 2x. But I would liken this to and here's why. What is e to the 2x? Well, that's e to the x squared, isn't it? So when you see an e to the 2x, it's really e to the x squared. Get used to it, really. It's honest, it's true. What this means is what? Well, we could factor this. To get e to the x squared, we'd have to take an e to the x times an e to the x. And factoring works like normal. What times what is 2? That adds together to get a -3, why a -2 and a -1. This then gives us not 1, but 2 possible equations. So e to the x equals 1, or e to the x equals 2, which means that x is equal to the natural log of 1, or x is equal to the natural log of 2. Now, I wouldn't expect you to know the natural log of 2 by heart, but I would expect you to know the natural log of 1. That's just 0. E to what power is 1? Well, it has to be 0. The natural log of 2, that's a little less straightforward. As a matter of fact, it is 0.693. Key thing here, recognizing that you've got two different terms, a squared term and a linear term, but in reality they're exponentials. Okay, so this is some just more practice. So I would exponentiate base e, let's say. So this would be e squared equals 3x, divide both by sides by 3, x equals e squared over 3, which is just a number. Leave it alone. Okay, both base 3 logs. If I exponentiate base 3, those will cancel, and I get 5x minus 1 equals, I hope you can solve a linear equation. Subtract x from both sides, add 1 to both sides, divide both sides by 4, x equals 2. Now, what I am going to do is I'm going to put this 2 back in here, because I can't take, when I'm doing logs, I can't end up taking a log of a negative number. 5 times 2 minus 1 is 10 minus 1, or 9, right? And when I plug 2 in here, I get 9, which makes sense because, well, I should get the same thing, but they're both positive, so it means that this is a good final answer, right? Sometimes that won't work out, and you'll get what we call An extra solution, or as your books and everything else likes to say, extraneous, which is just a fancy way of saying extra. All right, keeping going. Get the natural log by itself before you exponentiate, meaning get rid of the 5 by subtracting it, divide by 2, then exponentiate base e, cancels, or rewrite in exponential form. It's the same thing. X equals e to the negative 1/2, or 1 over the square root of e, which is just a number. Same idea here. This is equivalent to this because I divide both sides by 2. Now I can exponentiate base 5. Did you know that 5 squared is 25? Divide by 3. Now in this case, I'd leave it as 25/3 because if I had to actually divide that out and write the decimal, I'd have to round, less accurate. Okay. All right, this looks like a mess. Now, this is where we can use some of our properties to help us out. So what I'm gonna do is, well, first off, I see a couple of things going on. Natural log plus natural log. So I could combine these two, meaning I could combine these into a single natural log of x minus 2 times 2x minus 3, right? Equals, for this one, I could bring the exponent up, so it'd be the natural log of x squared. Remember, in order to exponentiate, to get the natural logs to cancel out, then I want to make sure to, well, what do I want to make sure to do? I want to make sure to get the natural logs all by themselves, nothing multiplied, and it's just one term on each side. Now when I exponentiate, I get this. Now, I hate to say this, but at this point we're looking at a quadratic, 2x squared, right? Minus 3x minus 4x minus 7x plus 6 equals x squared. Subtract x squared, because this is how we do things. We need to set it equal to 0. Then we can factor. And then we have an x, and we have an x, and we have a minus 1 minus 6, which means that x minus 1 equals 0, or x minus 1, 6 equals 0, which means x is 1 or 6. Now, I'm going to double check. I'm going to plug the 1 back in. So when I plug the 1 back in, I get natural log of 1, that's okay. 2 times 1 minus 3, that's negative 1. I can't take the natural log, so when I plug 1 back in, I get natural log of 1 minus 2 plus natural log of 2 times 1 minus 3 equals 2 times the natural log of 1. Here's the problem. This and this simplify to the natural log of negative 1, which does not work. We can't take the natural log of a negative number, which means that this is an extraneous or extra solution. Extraneous, which is a fancy way of saying extra. So that's an extraneous solution. So the only solution is x equals 6. Okay? And that concludes some examples.